You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Amir Siraj. Amir studies astrophysics at Harvard University and is interested broadly in theoretical astrophysics. He is a Goldwater Scholar and US Presidential Scholar. He is co-president of Harvard Students for the Exploration and Development of Space and former senior US editor of the Harvard Political Review. His research advisor is Professor Abraham Loeb. We're often asked how this show is made. And to be blunt, it takes a lot of preparation. Reading material is key to how John prepares for the show. That's why we're happy about being sponsored today by Blinkist. Blinkist will help you understand ideas, either from books or podcasts, in a relatively short amount of time. Recently, our producer Ross focused on learning more about unconscious bias and used Blinkist to get key takeaways from the Leader's Guide to Unconscious Bias, including learning how to identify it and what to do about unconscious bias when you do identify it. And with Blinkist Connect, any premium user can share their account with another person. Essentially 2 accounts for the price of 1, at no additional cost. Blinkist has thousands of titles, all condensed and in 27 different categories, put into either 15-minute text or audio explainers called Blinks. So try Blinkist for yourself to access valuable knowledge and great ideas quickly. Right now, Blinkist has a special offer just for Event Horizon. Click the link in our description to start your free 7-day trial with Blinkist and get 25% off a premium membership.
Amir Siraj, welcome back to the program.
Thanks for having me, John.
Now, Amir, you have a new paper out that's freshly inked, as it were, very new paper, that goes into the detail of how the interstellar objects, which there are now 2 candidates, one strong, one getting stronger, that seem to, when they enter the atmosphere, interstellar meteorites, they seem to be showing a sort of tensile strength greater than what you would expect from a solar system iron meteorite. This is above and beyond octahedrites and all those sorts of things that we normally see. So this could lead to several explanations that could mean new objects that we've never seen before in nature entering our atmosphere. And one of these is the idea of a supernova bullet. Could you lay that out for us?
Absolutely. So, as you mentioned, we identified a second interstellar meteor candidate in the CNEO's catalog. We first identified this object back in 2020 or 2021, I believe. And this impacted the Earth in March of 2017 off the coast of Portugal, basically between Portugal mainland and the Azores. And it exploded with the energy of about a kiloton of TNT. And much like the meteor that was detected in 2014, that the Department of Defense confirmed in 2022 as interstellar in origin, this was also detected by US spy satellites. That's why it showed up in that database. And it's also interesting to note this was still predating Oumuamua by about 6 months in the case of this 2017 meteor. And it was moving a little bit slower outside the solar system relative to the 2014 meteor, which we're now calling IM1 to distinguish between that and this one, IM2. And to put it in context, this object was moving at about 26 kilometers per second outside of the solar system. And it was also moving at about 40 kilometers per second relative to the local standard of rest. So a little bit less extreme dynamically than CNEO's 2014-0108. But what was interesting is that we did the material strength calculation, the same material strength calculation that we did for the 2014 meteor on this one. And in fact, we repeated this calculation for every single fireball in the database. And the way we did that was from the simple principle that as a meteor travels through the atmosphere, it experiences friction with the air, and so the dynamical pressure goes as rho, the density of air, times v squared, the speed of the object relative to the air. And then you can look at the light curves for these objects, which are published by the DoD, and find the dynamical pressure that corresponds to the peak power in the light curve, basically the altitude that the object breaks up at. And that means that crossing that level of ram pressure causes the object to deform and break apart. And so to sort of contextualize this, iron meteorites are the strongest ones that we know of in the solar system. They make up about 5% of all falls. And the typical strength in the atmosphere at which they break up is 50 megapascals. And so we computed the ram pressure at breakup for all of the 273 fireballs in the CNEO's catalog. And first of all, this sort of confirmed the fact that the 2014 meteor was a really extreme case. The last big flare, there were 3 flares. The last flare was at 194 megapascals. And so it was far and away the strongest meteor in the database. And far and away meaning by more than a factor of 2 compared to second place. And now the second place meteor in terms of strength was bound to the sun, but actually the third strongest meteor in all 273 fireballs reported by the US government happened to be this second object that might be interstellar, the one that was detected in 2017. And this object had a strength of about 75, I believe, 80, I have to check the paper, megapascals. So it certainly would be consistent with iron in a way that the 2014 meteor is a little bit more difficult to sort of make that conclusion, given that it's stronger than the typical iron meteorite, although it's still possible for the 2014 meteor. But this one looks much more like iron. But it sort of presents a puzzle, right? Because, imagine you're drawing meteors from a hat and, all meteors come from the same distribution. What are the odds that we pick such extreme values of tensile strength or material strength? There's 2 ways of looking at it. One is just saying, okay, you have 273 fireballs, and what are the chances of picking 2 of them, and they both happen to be in the top 3? This sort of simple combinatoric way of getting to the answer. And that turns out to be about 1 in 10,000. So it's a very small chance that even if you disregarded the actual numbers involved and you simply looked at what are the chances of getting 2 fireballs in the top 3 out of 273 objects, that's extremely unlikely. But we also checked another way, a more statistical way, by fitting a log normal distribution. Turns out the distribution of material strengths in this database, if you take the logarithm of those strength values, looks to be distributed normally. And so we fit a Gaussian to this distribution, and we asked, how many standard deviations away from the mean is the first interstellar object, the one that was confirmed, and the second interstellar object, the one that is awaiting confirmation. Turns out the IM1 was 3.5 standard deviations away from the mean, and IM2 was 2.6 standard deviations away from the mean. And when you combine that, you find that the chances of drawing those kinds of values from a Gaussian distribution is more like 1 in a million. So you can think of the chance of the fact that these objects were so strong being a fluke would be somewhere between 1 in 10,000 and 1 in a million. And so if this second interstellar object is confirmed, that sort of implies that interstellar meteors come from a different population with a material strength that's characteristically higher than meteors originating from within the solar system. And so that led us to think about some possibilities. And supernovae have been observed to produce iron-rich bullets, and those could be a possible origin of IM-1 and IM-2. In particular, if you look at X-ray imaging of the Vela supernova remnant, it showed that there were bow shocks from these clumps of iron-rich matter flying out of the explosion site, and we've seen that in other supernova remnants. So perhaps supernovae are populating the galaxy with clumps of iron that end up down the line turning into interstellar meteor. Basically, that theory would say that maybe IM-1 and IM-2 came from an exploding star, not a planetary system as most people tend to attribute the origins of interstellar objects to.
Now, if you could get a hold of material, this iron that is being generated originally in supernovas, could you really look at that isotopically and try to learn the ins and outs of how supernovas occur and what are the differences between different types and different circumstances from recovery of that kind of material?
Absolutely. Supernova modeling is notoriously difficult because we don't have a lot of specifics on the conditions involved, both the initial conditions and the sort of final outcomes. And actually being able to sample a supernova in this way, especially a macroscopic object, there's been detections of various isotopes that may be indicative of supernovae, but really getting the bulk composition of a supernova remnant would be enormous in terms of pushing forward our understanding of how stars explode, because then we can enter those constraints, those chemical constraints, and could figure out when the supernova occurred, what kind of star it was from. We could enter all of those constraints into our models and see how that changes the picture. Also, because there are many different types of supernovae, some aren't even fully understood why they end up exploding in the first place. So this would be revelatory in that sense. But it's also, if these end up being from supernovae, this also opens another interesting realm, which is that of cosmic accounting, or the cosmic mass budget. Basically, if you imagined you went around the galaxy and counted up how many of each element is found in stars, how many is found in dust, how much is found in planets. That's what I mean by cosmic accounting. And what's interesting is that if you require that IM-1 and IM-2, these two interstellar meteors, if you require that they weren't statistical flukes, and perhaps that these objects, this DoD observation program, at least the published results of the observation program that has given us these two interstellar meteors, have been operating, at full capacity for about a decade. So if you say that if we don't think that these two objects are statistical flukes, perhaps they should hit Earth once a decade. By making that assumption, you can sort of back out, these must belong to populations of objects. Basically, as we've discussed before, space is filled with interstellar objects. And you can ask the question, how much mass in iron do you need to make one or two of these objects, rather, hitting the Earth within a 10-year time span statistically likely? Turns out you need a lot of iron. You need about 26 Earth masses of iron per cubic parsec. And what's interesting is that if you count up all of the potential sources of iron, so there's stars and there's the interstellar medium, so stars and all the stuff between stars. If you count up all of the mass in those, and based on the metallicity of stars and the metallicity of the ISM, you can back out how much. Let's treat it generally. Let's say all refractory elements, so everything from iron to magnesium to silicates, so stony objects would be included in this too, not just metallic ones. If you check how much mass is there in refractory elements available from the baryons that we have in our galaxy, it turns out to be about 70 Earth masses per cubic parsec. And so this sort of implies that if this detection is in particular the second detection of this interstellar meteor, because the second meteor was 14 times more massive than the first, and not only is that relevant for ocean expeditions, as we'll discuss later, but it also means that the astrophysical implications in terms of the mass budget are enormous. More than a order of magnitude more important from the second object, because this implies that 40% or so of all refractory elements in the galaxy are locked in meter-scale interstellar objects. So if these come from supernovae and are not a statistical fluke, this means that supernovae are really churning out these refractory elements into this form that was previously invisible to humanity, and so that's very interesting. And obviously, if it's not a supernova, if the origin is not a supernova, it's very difficult to explain with planetary systems, because if you look at the mass accounting for planetary systems, you typically think of 1% of all mass, of all stellar mass going into planetary systems. And so this is saying you need to actually 40% of refractory elements. So planetary systems miss by, between 1 and 2 orders of magnitude.
Now, what of a kilonova?
A kilonova could definitely provide these types of objects as well. We know that kilonovae produce a lot of heavy elements, but definitely that's a possibility.
And that's even more interesting ultimately, because instead of an exploding star, it's 2 combining neutron stars, and one can wonder about what might be contained in a piece of iron from that.
Yeah, you might end up finding some gold in there too.
Gold, silver, all these elements, and you could get even wilder with it and say, well, is neutronium stable inside? Yes.
Only one way to find out.
Only one way to find out. And you're going to attempt to. The project to recover ISM-1 material from the first interstellar meteorite you guys identified is ongoing and fully funded now. So it's going to happen, right?
That's right. We just received full funding, and so now we are, we've been meeting with the full team, and right now we're in the process of identifying the right ship to take to the coast of Papua New Guinea, and also the timing of the trip based on the weather in that region, and when the ship's available, when our sled is going to be built. Basically, we're putting together all of the logistics now, which is a really exciting place to be.
What are the logistics of the sled looking like? I mean, obviously, if you're looking for iron, there's an easy way to recover that. So I imagine magnetism is going to play a big part. But what if it's something that isn't magnetic?
Right. So, I mean, if the object isn't magnetic, we are going to be towing basically a series of nets with different opening sizes, and so those will be able to scoop up material on the seafloor that might not be ferromagnetic. But most meteors, even if they aren't iron, do have enough ferromagnetic material in them to respond to a magnet, and so that's going to be our primary search method. The net will be attached to the back of the sled, but the sled itself, you can imagine it's just embedded with very powerful magnets and attached to a several kilometers long tether, and we'll be dragging this across the ocean floor. And so right now we have a 10 kilometer by 10 kilometer box that we're looking for these fragments in, and that's based on the uncertainty provided to us by the Department of Defense. They gave the location of the airburst to within 1 decimal place in terms of longitude and latitude. And then we did our own calculations to figure out the distribution that's expected on the ocean surface and on the ocean floor. Thankfully, winds were low, and also ocean currents were low at that time. And so that's very advantageous to us. So right now we have a 100-kilometer squared search box, and our current plan, basically with 10 days of operation, we can search about 1 kilometer squared total. So that's about 1% of the area. So our current plan is to crisscross, basically create a grid, because the sled is 1 meter by 2 meters, and so create lines that cover this entire search area. And if we end up finding something on a particular run, then we'll focus on that area and sort of hone in that way. We're also checking whether the U.S. government will provide us with better constraints on the location. It seems like the only reason they published to first decimal place was just in terms of convenience for the online posting of the database, and obviously the government has extraordinary capabilities when it comes to missile defense and sort of satellite remote sensing operations. And so if they gave us 1 kilometer uncertainty, think about it, like Google Earth gives you uncertainty of a few meters, or GPS a few meters. But if we just had 1 kilometer instead of 10 kilometers, then the search area would be reduced by a factor of 100, and we would be able to trawl the ocean floor of the entire search area. So we wouldn't need to crisscross or create a grid or have to go after an area where we start finding something. We would just simply search the entire area in that case. And so we're pursuing that as at the same time as organizing the logistics of the expedition.
Presumably, they want to keep the capabilities of their sensors secret for national security reasons, especially with missile defense. But is it possible that they could say, well, look, we'll give you the coordinates, but you have to keep that classified, but you don't have to keep the findings of the actual meteorite classified? Could a deal like that be worked with the government?
Yeah, that's definitely possible. It sort of depends on what they want to do. But I think that even if they made totally public this 1 kilometer uncertainty, I personally don't think that would be giving much away, because we know that the government does have, or even commercial satellites can do much better than that. But we're sort of going to them and asking if that can be improved in any way.
Now, there have been critics, especially Twitter was aflame for a time about the possibility of recovering an interstellar meteorite, and people were comparing it to lost airliners and things like that that could be anywhere in a large swath of the Indian Ocean, as opposed to something very targeted. But this is actually very targeted, and it has been done before. The NOAA has recovered a meteorite from the ocean floor in an analogous way. So what would you say to the critics that say it can't be done?
Yeah, well, it's they say that having critics can be a good sign, because it means that you're doing something worthwhile. In this case, we have basically the two key people who were involved in the 2018, the big expedition that you're referencing, that was successful in recovering a specific fragments of a specific meteor from the ocean floor. And those two people are Mark Fries. He's NASA cosmic dust curator, who's actually the first person I reached out to when I had the idea for doing an ocean expedition, and he was extremely helpful as an early advisor for the project. And he basically explained that the first question I asked him when the DoD letter came out was, is this even feasible? Based on your experience, I know that these expeditions are feasible in general because you did it, but what about the particulars of this case? And he said, actually, this case is even better because of the ocean depth. And I was confused at first. I said, well, it's a lot deeper. Where you went was 100 meters in depth. This is 1.7 kilometers. And he said, exactly. That means that the sedimentation rates are very low, and typically the ocean floor remains unperturbed for very long periods of time. And so once the fragments of the meteor fell to the ocean floor, they should have just stayed there over the past 8 years. If they were in shallow water, they could have been cast adrift or ended up on the shore of another continent, for example. And so it 100% can be done and has been done. And in fact, the other key person involved in the mission that was sponsored by NOAA is actually the person who was running NOAA at the time, Tim Gallaudet. He is the former acting administrator of NOAA. He was also oceanographer for the Navy and I believe Undersecretary of Commerce for the United States. And he is on our team. He's actually a co-author on the expedition plan paper, which was I was first author, Avi was second author, and Tim was third author. So we have, not only do we have the oceans and atmospheric expertise, but we have the people, the advising of people involved in a mission very similar to ours, and that shows that this can be done.
And above and beyond that, though, it's not like we haven't been locating shipwrecks for for time immemorial. I mean, how do you find the Titanic? Well, someone did, Robert Ballard. So even if you're looking at something that has way more than a 1 kilometer square area, you can find it, and it has been done, and routinely so.
Yeah, he actually offered us his ship, Bob Ballard.
Really?
Yeah.
Well, you got to wonder about something like, okay, I mean, could you search the ocean floor remotely, not using a sled, and looking for magnetic anomalies like you would for a shipwreck? I mean, could you do magnetometer studies to try to find it?
Yeah, certainly. I think if you had a large impact, and what gets difficult in this case is that these fragments are expected to be so small, right? Because this the meteor was about the size of a microwave, and we think the fragments are going to be like, say, millimeter sized. And so at a depth of 1.7 kilometers, that gets difficult to do remotely. But I certainly think if you have a combination of a larger impact and shallower water, and obviously if it's shallower water, then you need it to be recent in time. But you could definitely do remote studies in that case.
The larger size of the second object, which I know it's early in the game on this one to start talking about recovery there, but what are your thoughts there? I mean, would that be a similar situation or even easier due to the higher mass?
Yeah, so the second object is quite exciting to me. This higher mass is good in two ways. One is the sort of astrophysical implication that I was sort of laying out, which is that it implies that interstellar meteors are a lot more important in sort of like, where is all of the iron in the galaxy? Well, a lot of it might be in interstellar objects that are about the size of a refrigerator. But the other area is exactly as you say. It would be a lot easier to find, and in fact, it might be possible to find a larger fragment of this second meteor. So it was 13 times more massive, and it was also traveling slower in the atmosphere when it exploded. And so those two things combined make it more likely that larger fragments survived and are currently sitting on the ocean floor. And so that's really, really encouraging. And we're definitely going to be going to the coast of Portugal after as sort of the next step beyond this expedition.
In regards to what data you have on these two objects, and in regards to Oumuamua was weird in that it was sitting at the local standard of rest. Can you sort of infer if these were as well, and that these might be related in some way to Oumuamua?
So the orbits of these two objects were actually quite different from Oumuamua. The 2017 meteor IM2 was traveling at 40 kilometers per second away from the local standard of rest, and IM1 was traveling at 60 kilometers per second away from the local standard of rest. Typical stars travel at 20 something, or let's say 30 kilometers per second away from the LSR. And so in particular, the 2014 meteor was an outlier in the opposite way from Oumuamua. It was traveling extremely fast relative to local stars, and so that fewer than 5% of stars have that kind of speed, and so that implies that it was ejected with a high speed, and so that's interesting. Almost from the other end, as like both being close to the LSR and being far away from the LSR are interesting. It's the stuff in the middle that's more typical.
Well, it's interesting because of, Supernova Bullet, and with that kind of velocity versus some other kind of object, which to me is starting to hint, just barely starting to hint, that there may be many different kinds of interstellar objects that we're only beginning to imagine now. There could be a whole mixed bag, so to speak, of flotsam and jetsam flying through the galaxy at any given time, right?
Exactly, and that to me, like, the very different properties that we've seen of the interstellar objects so far. I mean, look at Oumuamua, right? You had extreme variations in the light curve. You had non-gravitational acceleration without evidence for a cometary tail. The speed was very close to the LSR. Then you had Borisov, which appeared exactly like we would expect an interstellar object to appear, probably from a exo-Oort cloud, icy, very large, prominent coma. And then we have the first interstellar meteor, extremely high material strength, unusual dynamics, very, very fast relative to the LSR. And then we have the second interstellar object, which is still quite strong, not as dynamically unusual, but way more massive, right? So each interstellar object, or in the case of IM2, interstellar object candidate we've seen so far, brings a different set of attributes to the table that imply different composition and potentially different origins. And it's really exciting because it shows how the study of interstellar objects is really a new window into astronomy, because my hope is that it's going to shed light, the field will shed light into all different areas of astronomy. If these meteors are from supernovae, it'll tell us how stars explode. Then, you'll have objects like Borisov, which clearly come from planetary systems. That tells us how other planetary systems form. Then, you might have some objects that are artificial in origin. We might have exotic objects like halo meteors, basically meteors or macroscopic interstellar objects originating from the galactic halo. And these are the oldest stars in the galaxy. Avi and I sort of proposed this in a paper a few years back, and these would allow us to learn about the conditions under which the first planets formed. Then you could have objects made of pure hydrogen ice, like those proposed in a series of papers a couple of years ago. There's a whole host of new astrophysical objects that we could study for the first time, and then learn much more about the universe as a result from.
That's actually a surprisingly spooky thought to me, that if you get materials from when the first planets formed in the Milky Way, when it was first capable of doing that and creating planetary systems, you could look and see if the chemistry of life was there. If you start seeing phosphorus and carbon compounds and things like that, then it could, as far as astrobiology goes, push back the possibility of life in the Milky Way much further than it is. Or maybe it's just a recent thing, right?
That's a great point. Yeah, and these things would be actually very easy to identify based on their speed. The galactic halo stars, even though they're very rare in our neighborhood, they they have a distinct kinematic signature, which is that they travel at hundreds of kilometers per second. And so if we saw and wouldn't get slowed down along the way. And so if we saw, like, for example, if you have a supernova remnant, it could get slowed down, but because of all the material that surrounds it. But these objects from the galactic halo wouldn't be slowed down. So basically, if we set up an interstellar meteor observation program of our own, with cameras and satellites, whatever, you just wait until you see an interstellar meteor that's traveling at a couple hundred kilometers per second, and that's from the galactic halo. So they should be very, very distinct in that sense, and then studying the composition will deliver really salient insights, as you sort of outline, about the timing of the chemistry for life. And these first planets, actually, Avi wrote a paper with someone a few years ago about these first planets. They might have been composed primarily of carbon. They were probably very different from the planets that we see today, because these objects were very poor. These stars were very poor in heavy elements.
Now, along those lines, can we characterize an exoplanet like that, an early one like that, with an instrument like the James Webb Telescope? I mean, can we look at something and say, composition here shows this planet is almost a fossil planet? I mean, can we do that, or is that still a step too far?
I am not sure about the fine details on this, but I do believe that it's within the realm of JWST, and so that would certainly be extremely exciting, and so I'm sure that people are already have probably already put in proposals, but if it's not within the realm of JWST, it'll probably be within the realm of the next big telescope.
Now, efforts to maybe look at our vast meteorite collections on Earth, are you guys looking for anomalous meteorites that have already been recovered that might be of interstellar origin?
Yeah, so that's a really promising area if you think about, like, philosophically, right? Because these, we identified one that's for sure, one that's a candidate out of 273 objects. Like, that's a fairly large number of fairly large percentage in the grand scheme of things when you think about how many meteorites have been recovered. So yes, that is definitely of interest to us, and I think that, like, it becomes more concrete when hopefully we're able to find samples of IM1 and then eventually IM2, and then we can sort of know what to look for. I mean, we can also take the approach of just, like, looking for things that are out of the ordinary, but once we have telltale signatures, maybe like chromium isotopes or way off or something, when we have these templates given to us by physical samples of interstellar meteors, I think that'll be the most fruitful time to start scouring every meteorite collection on the planet.
So, in other words, you need to know what you need to look for before you actually go through the task, but it's an extension eventually of doing this. And once you recover any interstellar material.
Yeah, exactly. Then we go to our museums and we figure out if we already had something like it, and that we maybe we missed a needle in a haystack or many needles.
Well, and there's always the question too about just how thoroughly iron meteorites in our collections have been studied, because they're notoriously harder to do than the chondrites are. So I don't know how much work has actually been done as far as looking at the isotopes and such in existing iron meteorites from the solar system anyway.
Yeah, I think this would definitely, especially if we found something metallic, this would definitely ignite a lot of interest. Everyone I've talked to so far, every planetary sciences professor or anyone with a laboratory that does this kind of work that I've spoken with so far has been extremely excited about the possibility of analyzing anything that we recover. So I do think that it will reignite interest and probably bring new interest in terms of analyzing existing meteorite collections.
And it speaks to interstellar objects in general because we are being delivered a sampling of the entire galaxy right here at home. And not only going out and catching up with things like Oumuamua or future detected interstellar objects, but also interstellar objects here on Earth. And we can basically do a survey of the galaxy, chemically anyway, and from an armchair, basically.
Nature's making it so easy for us. It's really taken all the work out of it.
It really has. But at the same time, there's another possibility, and I have to mention it because people will ask, is the idea of a technosignature being found this way. Do you think, if such a thing were found in the form of an interstellar meteorite, it would stick out like a sore thumb, right? You would know instantly that this thing was not of natural origin, right?
Oh, yeah. If we found like an alloy or something that doesn't occur naturally, that would be a telltale sign. And so, obviously that would be extraordinarily exciting and would sort of, that would rewrite human history, not just be a really exciting scientific discovery, but it would be important, philosophically and anthropologically. But what's good about this method is, unlike some other versions of SETI, which can be a little bit more ambiguous, let's say you find, or not even SETI, just like all forms of, search for life, just broadly, not just technosignatures, but biosignatures. The issue with a lot of like remote sensing versions of the search for life is that, there's going to be endless debate. If we see a planet that has oxygen on it, or if we see like
phosphine,
a radio wave transmission, or if we take phosphine for example, the debate is going to go on forever at when the first candidates roll in. And so what's exciting about looking at physical samples is it's a lot more cut and dry, because you can check the chemical composition and you can know whether that occurs naturally or not.
Unambiguous, and that's the key to anything SETI, is you have to have no ambiguity. And with a sample, there wouldn't be any. You would just be able to say, aliens have aluminum.
Right. Right.
Which may actually end up being disappointing, because if you found, as Avi says, a Pepsi bottle, yes, it would be astonishing, but at the same time, it's a Pepsi bottle.
Right. Hopefully, we would find something more exciting, something like if we would hope that if aliens are sending us something, that it might be some type of alloy or I don't know, contraption that we haven't seen before. Otherwise, we'd be a little disappointed.
What would be fun is if it's something weird, like a piece of graphene, or something,
right.
Something that we don't quite have yet, or something like that.
That would be helpful, yeah.
So when is the expedition off Papua New Guinea? When is the sort of time frame for that? When are you guys going to head out?
Yes.
Or do you even have any idea?
So it really depends on the boat, and we're surveying a few different options right now, but definitely within the next year. So could be as soon as a few months from now. We're ironing out the logistics right now, and basically hoping to set sail as soon as all of the logistics are taken care of.
So do you get seasick?
I don't get seasick, but sometimes I get car sick. So if this ends up working with my schedule, I'm going to bring a lot of Dramamine.
Hopefully you won't need it. I've actually found that while I get car sick, I do not get seasick. And it seems to be two different sorts of motion sickness. So maybe you'll get lucky like I did. But, well, best of luck.
Fingers crossed.
Yeah, fingers crossed.
Yeah.
Best of luck, though, on the expedition. And come on back anytime and keep us updated.
Thanks so much, John. I'd be delighted to.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.